Our goal today is to help you improve your induction sealing operations by developing an in-depth understanding of the critical interactions between your liners, caps, cappers, and induction sealers. We are extremely fortunate today to have an expert panel representing each of these unique components for successful induction sealing. These gentlemen have worked on projects spanning the United States, Canada, Puerto Rico, Europe, Middle East, Asia, and Australia. Alan Schuheibar is the president of Bellatrix. He has 19 years in the packaging industry with a focus on pharmaceutical, nutraceutical, cosmetics, and personal care applications. Alan is the chairman of the Business Intelligence Committee at PMMI, the group which is responsible for all industry reports generated by the organization. Tim Farrell is vice president of sales and marketing of Phoenix Closures, the largest privately held cap and closure company in the U.S. Tim has over 20 years experience in the packaging industry and 18 years with caps and closures. John Brown is the vice president of business development of Seelig Liners. John joined Seelig in 2010, having spent the prior 18 years with various closure companies, the last of which was Closure Systems International. John has held roles in product development, operations, general management, and marketing. Jeff LaGrange is Enercon's Cap Seal product manager. Jeff has over 20 years experience with Enercon and is intimately involved in the design and development of Enercon cap sealers, and is in communication with packaging professionals regarding their induction sealing challenges on a daily basis. Ryan Schilke is Enercon's sales director and has over 17 years of experience in the packaging industry. He is a member of the board of directors for the Association of Sauces and Dressings and is also a member of the PMMI Global Marketing Committee. To begin, we want to preview what these gentlemen will cover for you today. We'll review the principles of induction sealing operations. We'll learn about selecting the right liner for your application. We'll learn how to ensure that your cap, liner, and bottle are compatible for induction sealing. We'll understand the benefits of different capper styles. We'll find out how much torque your capper should apply for induction sealing. We'll learn how to set up an operating window for your induction sealer. And at the end, we'll have an open forum where you can get expert advice on how to achieve a perfect seal. I'd like to begin by introducing Ryan Schilke, who will cover the principles of induction sealing operations.
Thank you, Mark, and thank you everyone for joining us today. We're going to start the webinar kind of on a high level and discuss basic principles of induction sealing that apply in any application. First piece we're going to talk about is one of the critical components, one of the critical pieces to understand, and that is the theory of pressure, heat, and time. Any sealing process that you undertake in your operation is going to require those three elements. So let's dive into each of them a bit deeper. Pressure in the induction cap sealing process is very critical. And the pressure that is applied from the cap to the lining material and then which puts it in intimate contact with the bottle is provided by cap application torque. We're going to talk a lot about cap application torque throughout the webinar today, so keep this piece in mind as we go through. The heat component in the induction sealing process is generated by the induction sealer itself. And the picture on the screen here illustrates the magnetic field that's created by the induction sealer. So you'll see the little white arcs coming from the center towards the sides of the sealing head in this picture. That indicates how that field generates throughout the width of the coil. This happens to be a case where it's going to be a wider application. It happens to be a 63 millimeter closure, and the heat is going to be varied based on the power level you set the machine at. The final component in pressure, heat, and time is obviously time. And time for this is not necessarily in minutes or seconds, but it is dictated by the conveyor speed, by the belt speed in which your product is running on. So we'll take a look and say if you're running 50 feet per minute, we'll size the machine appropriately for 50 feet per minute, as well as knowing your cap diameter and the cap style involved. As we talk about time, an important thing to remember here is that the relationship between this pressure, heat, and time equation is not linear. If your product is running at, let's say, 100 feet per minute, and you decide to increase that by 10% to 110 feet per minute, what you've got to keep in mind is that the relationship then between the power level needed on the machine is not necessarily linear. There are cases when it does happen, but it's always important to run and qualify your operating window, which Jeff from Intercon will get to a little bit later in the presentation. So let's talk about a few variables in the induction sealing process, the first of which is air gap. And when we talk about air gap, what we're referring to is the distance from the foil is from the sealing head, or the top of the closure from the bottom of the sealing head. This is important to be consistent. The gap can be 1/8 of an inch, which is something we often recommend. Sometimes it's 1/4 of an inch, completely acceptable as well. It could be 1/2 an inch. 1/2 an inch probably isn't going to be overly effective. You're not going to use your machine as effectively. But the most important thing with your gap is that it's consistent. And we actually provide a tool with each of our systems. It's actually about an 18-inch ruler, 1/8 of an inch thick. You set 1 or 2 of them on top of a bottle on either end of the machine. Simply lower the machine down, and that will set your air gap consistently each time. And Jeff, again, will dive into that a bit more later. Cap height is an important variable. When you're talking about a common flat or continuous thread closure, the foil, if you look at a cross-section of that, the foil is right near the top of the closure, which makes getting that magnetic field we're creating very easy to get into the foil. Same thing with the child-resistant closure. It's a little bit deeper, but again, it's pretty easy. It's when you get to specialty closures like the dispensing closure here that we see on this bottle of mustard. You'll see 2 arrows, one pointing at the top of the closure and another one pointing at where the foil actually sits in this package. So we're talking here, you're probably somewhere between 1/2 an inch and 1 inch of cap height, which ultimately translates to that distance in air gap as well. In these cases, it's important to note that you're doing this in your application, and we'll design the special sealing head for your application to make sure we can be just as efficient as possible. I mentioned it in the pressure, heat, and time component, but application torque, I'm going to mention it again. We're going to dive into it deeper, but this is the most critical component to get right in your induction sealing process to ensure every time you're as consistent in your seal as you'd like to be. The final variable that I want to talk about is material change. And this can be anything from a wholesale material change, maybe that's your packaging, your bottle in maybe an HDPE bottle and you want to change to PET, or it could be simply changing from supplier A to supplier B. It's important to note any of those changes and make sure you run compatibility tests with the induction seal material and the bottle that you may be changing, or if you're changing cap suppliers, that the lining material stays the same so that piece does not come into effect and ultimately change your success in the induction sealing process. So now I'd like to hand it over to my friend and colleague at Sealing Liners, John Brown, to talk a bit more about liner selection in the induction sealing process.
Thanks, Ryan. And before we talk about leak prevention, wanted to just thank Intercon for coordinating and spearheading this, what promises to be a very informative webinar. And before we talk about selecting the ideal liner, we need to think about what the benefits that a liner provides so you can customize your selection. The best liner for you is really the one that most efficiently meets your needs. Originally, liners were used for leak prevention, and that's still the most common use of liners, but they've also provide other benefits as well. For instance, with induction seals, They provide consumer confidence that the product that they are purchasing is safe and secure, all the way to the extreme of providing tamper evidence. Induction heat seals do meet the tamper evidence requirements for regulated products, such as analgesics and pharmaceutical products. Liners also provide a hermetic seal, essentially zero gas transmission and zero moisture vapor transmission. And what that means is it keeps the good stuff in, like fragrances or active ingredients, and it keeps the bad stuff out, especially moisture for products that need to be dry, like powdered coffees and granules. And also it keeps out oxygen for those products that are oxygen sensitive. We have several applications where the liner is actually being used as a means of anti-counterfeit. These are typically for products that are more expensive or ones that have very complex and varied distribution where it's easy for the counterfeiter to introduce their product. It's not a huge problem yet in North America. This tends to be more of a Eastern European and Latin American issue with things like pharmaceuticals and liquors. However, it's becoming a much more significant problem in North America. So we've just talked about what the benefits that a liner can provide. Now we'll talk about how to really select the best liner for your application. No one liner is a one-size-fits-all, so to speak. Liners are engineered laminates, the simplest being a 3-layer structure to the most complex being 8 or more layers. For instance, Sealig has over 1,000 stock offerings. So first step is, and Ryan mentioned this before, is selecting the correct heat seal layer. That's the face, we call the facing that goes against the container. Your heat seal facing must be compatible with your container material, be it PET or HDPE or even glass. Heat seals are customized for the specific container material. The second step is considering the package contents. Some products, agrochemicals and other chemicals, are quite aggressive and you may need a barrier. Other products are more inert and don't interact as much with the liner material, so you can go with a standard non-barrier liner. The third thing to consider is the filling conditions or post-filling package treatment or even distribution. In the case of hot fill, cold fill, and things like retort, there's a significant amount of potential energy transfer, and that needs to be considered as we're going through an induction sealing process, which uses heat as a means to seal the induction liner. Also, if you have a product that's being distributed or filled at a low altitude and distributed to high altitude or vice versa, you need to consider that to make sure you have the right structure mechanical structure in your liner. The fourth step is looking at your seal and if it requires tamper evidence or not. Clean peel is more typical. However, tamper evident, if your product requires tamper evidence or you want tamper evidence, that needs to be considered up front. And basically the tamper evident liner, the bond is stronger than the structural integrity of the liner itself, and that's how tamper-evident liner is created. The fifth step is looking at your reseal integrity. After the foil has been removed by the consumer, does the package still need to have a superior seal or reseal against usually things like oxygen or moisture? And this is accomplished through what we call a two-piece liner. To save the closure manufacturer from having to punch two different materials and insert them into the closure, we sell a two-piece liner And if you see the graphic on the left, the schematic there, on the bottom you'll see the foil inner seal, which stays bonded to the container. And then on the upper side you'll see a reseal liner, which stays in the closure. And there's a wax bond between the two. It's a temporary wax bond. As the foil induction seal is heated up, the wax melts and it's absorbed into the reseal liner, allowing the reseal liner to stay in the closure and the foil inner seal to stay with the container itself. And lastly, the last step is really looking at the backing material. The backing typically is either a thin paper, a little bit thicker board, or a foam, and these are needed. The selection is really based on the needs. As far as the backing goes, it's required for liner retention. If you don't have a backing, the liner's not resilient enough to stay in the closure as it's inserted and punched. Also, the induction, the insulating heat, you need to insulate the heat of induction from the closure, and that's what the backing does. Also, it applies the even seal pressure, and we'll talk about torque in some later presentation, and also peel integrity. Without a backing, the foil would tend to rip, so it needs something to keep it together. So now we have a good seal, and the consumer is going to engage that, and we have many options for a positive experience for the consumer. Typically, a side tab might be presented to the consumer to remove and peel off the foil. However, too long of a seal or wide of a side tab can prevent the consumer from pulling it off by having that side tab. If it bonds to the side of the finish, it's very difficult to remove. We recommend a top center type seal, or tab rather, which allows the consumer to grasp that center tab and pull it up, such as our Lift and Peel or Top Tab brand liners. The other advantage besides consumer convenience on removing the seal is also this avoids having the consumer be in contact with the seal surface. For things like chemicals or toxins, or maybe just a sticky substance like syrups or honeys, the consumer's finger is not in contact with that. Also, there's an opportunity for defending your product against counterfeiters with anti-counterfeit means. Overt counterfeit means are typically visible, and they're usually intended for the consumer, so you know you have an authentic product. The covert or secret is non-visible, and that's really for the supply chain retailers to be able to evaluate that product that's on the shelf and audit it and make sure it's authentic. They can use this information and to go back and determine where, in what region, and what specific retailers maybe if there's a counterfeiting problem. Lastly, the brand owner has an opportunity here. The liner itself is a potentially a large piece of real estate that's a blank canvas. This is the last contact that the consumer has before enjoying that product. So it's an excellent opportunity to promote your brand through either couponing. We've done instructions. We've done even 2D barcodes that will allow your consumer to go directly to your website for more information. So in the end, what's the best seal? Well, that really depends on the function and the details of the application itself. With knowledge, you get success. If I were to take a survey and ask which one of these two seals is the best seal, picture here, I'd probably get a 50-50. But if I told you that a seal doesn't have ear flaps, it has just ear holes, you'd probably select the animal on the right. So with knowledge comes success. And you didn't probably think you'd hear any about zoology here, but a little lesson in zoology. With that, I'll hand it over to Tim Farrell of Phoenix Closures.
Thanks, John. Typically, induction seals are going to be delivered to the package by being inserted into the closure. So I'm going to give a little bit of roll on the caps roll, a little bit of a overview on the caps roll, delivering the induction seal to the package. I'll also talk a little bit about some of the potential failure points. In preparation for today's event, I spoke with a number of experts in our organization. Jeff Roddy, our Director of Technical Service, and I agree that the number one cause for failure of induction seals is torque, or more specifically, the lack of torque or the lack of consistent torque. Just a couple of weeks ago, 2 weeks ago, we were out visiting a medium-sized food manufacturer who had an 8-head capper, and they were experiencing about 10% failures in their induction seals. They were convinced that there was some problem with the induction seal material, but Jeff was able to very quickly start measuring torques on the line and discovered that of the 8 heads, one head of that capper, one of the 8 heads, was applying little to no torque. So the reality was they were getting about 12.5% seal failures, all because of a lack of torque. In this slide here, I show that one of the most important pieces of equipment on a capping line is the torque meter, or a measurement device for torque. By applying caps at a known and recommended torque, and then getting an immediate, which we would consider to be about 1 minute removal torque prior to induction, you can easily correlate your removal torques to the application torques for your capper. That is a critical component in assessing your seal integrity and where you might be considering or finding some failures. The other area is to make sure that you have 360 degrees of thread engagement. From a cap molder's perspective, it is easier to mold a cap that has 360 degrees or less of thread engagement. But for induction sealing, having at least 360 degrees or more is critical. As Ryan had mentioned in his presentation, pressure is the key to a good seal, and that pressure is created by torque. Getting 360 degrees of full engagement between the cap and the container allows you to get the pressure you need for consistent seal application.
Hey, Tim, I've got a question as we talk about 360 degrees of full engagement. Could you explain that a little bit more?
Well, typically what you'll see in caps are either going to be molded as a strip molded cap or as an unscrewing molded cap. An unscrewing molded cap is going to give you 2, 3, maybe 4 turns of thread in the cap. That'll match up with the 1, 2, or 3 turns of thread on the bottle, and you'll get at least 360 degrees of engagement. You can look at other closures that are molded with strip molded applications, and it's difficult to get more than 360 degrees of thread in that cap itself. So it's going to have to match up with the 360 degrees that are typically on the bottle. So that overlap, making sure we have 360 degrees all the way around the package, is key. Another way to enhance the pressure application or the pressure portion of the successful seal is to concentrate that torque and that pressure on the land area of the container. In closure, you'll typically see, as in this picture indicating, a series of seal rings. And these seal rings are designed to concentrate that pressure right on the land area of the container and, in effect, enhancing the pressure and providing an effective seal. It's also important to understand that liners are going to be retained in the cap and delivered to the package before induction sealing. So the process begins with a roll or a web of liner material that is punched into a specific shape and a specific size, and that size is chosen and determined based on the particular closure in use. Those cutouts are then inserted into the cap with automated machinery. You can see in this picture on the left we have that web of material with all of the punch outs, and on the right you can see that we are cutting out either a round disc or a disc that has retention tabs on it. That kind of leads me to how do we retain the liner inside of the closure. There's a number of different ways to do that. Typically liners are retained in one of 3 different ways. One is with an adhesive or a glue. The other way is to friction fit the liner into a specifically designed retention well designed into the closure. The third way is to friction fit that liner into the cap using retention beads and tabs on the liner itself. You can see in this picture on the left, we have a round disc that is being retained in the closure with a retention well, and then on the right we have a similar cap where the liner is being retained into the closure using tabs on the side. Although it goes without saying, storage conditions can have a huge impact on their liner capabilities long term. I think it's important for everyone to use FIFO, certainly as they rotate their inventory, but certain liners are susceptible to certain environmental conditions. Two-pieced liners, such as John was talking about, that are held together with a wax bond, are very susceptible to heat. So keeping those in a controlled environment is critical. That temperature should be between 60 and 86 degrees Fahrenheit. 2 years ago, we had a complaint come out of the field for failures of a wax-bonded liner. And the customer was certain that they were keeping their inventory in a air-conditioned, environmentally controlled warehouse and couldn't understand how there could be some heat. As we did some investigating, we found out that some of their caps ended up being stored right next to the place where they kept their forklifts. Propane-fired forklifts were idling within literally inches of where they were storing their caps. And as a result, they were causing heat problems in that wax layer. Other problems with storage can be particularly noticeable with paper or pulp-backed liner materials that are susceptible to humidity. The recommended humidity levels in your warehouse are going to be between 40 and 60%. Anything above that, you may have the problem of liners beginning to curl, and if they curl far enough, they can come out of the closure. The last thing I wanted to touch on is really that whole concept of putting together a consistent package, especially if you're putting together a package that is designed for consumer convenience. You've done a great job coming up with a bottle design that is easy for the consumer to grip. You've chosen a closure that is easy to be removed. It has knurling designs, or it has an easy removal feature, easy grip feature on the closure. The last thing you want to do is put in a liner, an induction seal, that requires that the consumer break through it with a household implement. You don't want to put a weld sealed onto this package that you've done a lot of work in making sure that it's easy to get into. So the last thing I want to show is we'll talk about this at the end of the webinar. There's a giveaway we have here for a cap gauge, an easy device to measure the diameter of closures, measure the diameter of your container, but more importantly, it gives the recommended torque for just about every closure size out there in the industry. With that, I'm going to turn it over to Alan Shohaibar from Beatrix. He's going to talk about the capper's role in induction sealing.
Thank you, Tim. Over this next section, I'd like to talk to you about how to optimize your capping process for successful induction seal. In a basic format, let's talk about the capping process, and the next slide will discuss the process of capping. First, there is the sorting of the bottles and caps. The caps are typically sorted with a vibratory bowl, a centrifugal bowl, or sometimes a cascading elevator, while the bottles come into the capping machine or the capping system using a conveyor, a star wheel, a feed screw, or sometimes side belts. The cap placement, this is where the cap meets the bottle. And this is a critical part of the capping process, which we will discuss a little bit later. Cap inspection, if available, gives a lot of great value to your capping process. Cap torque, and that is where you achieve the required torque. And if available, cap torque verification gives you the security that you are achieving the right torque. The next section, we'll talk about different capping methods. Capping could be done by hand using a single station torquer, using spindle cappers or belt cappers. There's also chuck capping and rotary capping. And over the next couple of slides, we will talk about them in a little bit more detail. In the most basic format, hand capping is where the operator places the caps and torques them onto the bottles. Now, although there's no capital investment in this scenario, there's a recurring cost of the operator being there. There's a risk of injury due to repetitive motion, and the torques that are applied are rarely consistent, which may cause problems for induction sealing later on. This process cannot be validated in industries that require validation, and the speeds are fairly limited, maybe 10 to 20 bottles a minute with a good operator. The next capping method is using a torquer. And by torquer, I mean a single station, either on a conveyor or with a handheld device. The operator places the caps by hand onto the neck of the bottle, and the torquer would apply the torque. Now, the operator is still required, and therefore there is a recurring cost going forward. It's a lower capital investment. There's still a risk of injury due to the fact that the operator would have to continue to apply the caps manually. The placement of the cap is typically inconsistent, and without any further verification or inspection afterwards, this process also cannot be validated, cannot be repeatable. And also the speeds are fairly limited, 20 to 30 bottles a minute. Spindle capping is the next level of capping. Here, the spindles or discs make contact with a cap, and they spin the cap onto the neck of the bottle. Now, this is a less expensive capper, and the bottles do not stop. The belts grab the bottle as they come into the system, and they guide them through in a continuous motion through the capping process. Now, due to the point-to-point contact of the different spindles or discs with the cap, the torques sometimes would be inconsistent because there's not a lot of grab between the spindle and the cap. There's also a high rate of cross-threading, 10 to 15%, and that is due to the fact that the caps are typically picked up on the fly as the bottle is coming through. The neck of the bottle makes contact with a cap that is positioned on an angle. The cap is typically not rotating at that stage and causing a high level of cross-threads. Spacing of bottles is required because you cannot put too many bottles through the system. And also, the speeds of this machine can be quite high in terms of 200 bottles a minute or so. Next slide, we'll talk about the belt capper, which is very similar to the spindle capper. However, it's belts that make contact with the cap instead of spindles. Now, although it's slightly more expensive, it offers benefits. And the benefits are that the belts can form around the cap, making more contact and therefore better torque control. Nonetheless, there is still a high rate of cross-threads due to the fact that the same mechanism of cap pickup is utilized in most cases. Speeds could be high. However, it is limited to one cap at a time, making contact with the belt to be able to control your torque properly. And therefore, it could be slower than a spindle capper. The next capper is an intermittent capper that we'll look at, and that is a chuck capper. Here, the cap, rotation, and application is perpendicular to the neck of the bottle. Now, although there are change parts required, typically they're not expensive. The torques are very consistent because only one chuck makes contact with a cap, and therefore we are able to achieve the desired torque consistently. One point to mention with chuck cappers is that the application of the cap is perpendicular to the neck of the bottle. The cap is typically spinning and synchronized, the rotation of it is synchronized with the threads so that the cap actually floats onto the threads as opposed to being slammed on. Here, that would allow us to reduce the level of cross-thread down to 0.5% or 1%. Mind you, the speeds on the chuck capper, since an intermittent motion machine, are limited. It could range from 60 to 120 bottles per minute. And finally, the rotary cappers offer continuous motion. There's typically multiple heads, 4 or more, which come in contact with the cap and bottle. It's relatively more expensive than the other capper models that we've talked about and require change parts. However, the high-speed capabilities of a rotary capper make it fit for specific applications. Again, here, the torque application is perpendicular to the neck of the bottle, and therefore we're handling one cap at a time, and that allows us to be precise with the torque application. Over the next few slides, I'd like to talk to you a little bit more about some capping considerations. The cap placement station is probably one of the more critical components of capping, and that's where cross threads happen if not handled correctly. There are certain types of caps, like embossed lettering caps, Yorker caps, snap caps, or caps with tabs or flip tops that require a certain types of cappers, where chuck cappers and rotary cappers may be better suited solutions as opposed to spindle and belt cappers, which will interfere with the tabs and the cap pickup. Now, I talked about it before, but I want to elaborate a little bit more on that now, and that is the angle pickup of a cap. When the neck of the bottle comes through and picks up the cap on an angle, typically the cap is not rotating, and a device pushes the cap onto the threads, and then the cap is spinning. That is the case with belt cappers and spindle cappers. That often is done due to speed constraints, trying to achieve higher speeds. However, the cost is higher cross threads. In chuck cappers and rotary cappers, since the rotation of the cap application motor, the down speed, are synchronized in a way to allow the cap to float onto the threads, and therefore limiting the number of cross threads. The next slide, we want to talk about the inspection. If available on the capper, it offers great value. This section will allow you to inspect if there is a cap present, if there's any cross-threading that took place. Is the cap high, which is common in CRC caps or child-resistant caps, and allows you the capability to tell the capper what do you want to do in each scenario. Do you want to reject it? Do you want to stop the machine, or do you want to ignore it? In previous sections, we discussed the application and removal torque, and the next slide will talk about these torque considerations. The application torque is what the capper applies onto the cap, and the removal torque is what you are able to test with the torque tester that was mentioned previously. One point I want to bring up here is immediate removal torque. It is important to note that when testing for removal torque, you need to set a time factor in terms of how long after you pull the cap offline you need to measure the removal torque. The longer you wait, the more the relaxation will take place in the liner and cap, and therefore the torque values might be different. There's 3 ways to apply and control torque onto the cap, using mechanical clutches, magnetic or pneumatic clutches, and servo motors. The mechanical clutch wears over time and needs constant adjustment, and also requires some trial and error to achieve the torque that you're looking for. Magnetic clutch does not wear over time. However, it still requires the trial and error scenario. The servo torque motor offers superior torque control capabilities, which we'll look at in the next slide. What's important to note here is that it provides immediate output, and that is when you're using a servo torque, it provides immediate torque output. What I mean by that is that when you set the torque value that you want applied onto the cap, the first cap out of the system will be at that torque, and therefore there's no trial and error in this scenario. Also, it gives you some diagnostic capabilities, such as low torque inspection. If you look at the chart that I'm showing here, you can see the green line shows the value of torque. Actually, we're looking at amperage here, but it represents the value of torque that is achieved. And maintain or sustain torque, this is a 3-bottle cycle that we're looking at. and it allows you to reject the bottle if you don't achieve the torque requirement. The yellow line in this chart shows the revolutions per minute, or the RPM, of the torque motor. The ability to monitor this type of chart in the background, in the software of the system, allows you to eliminate the initial impact of the chuck with a cap, and therefore preventing any erroneous readings of torque. Allows you to control the downforce. Very little downforce is required if you have the right solution. And also if there is any slippage between the chuck, the neck, the capper, the gripper, that allows you to reject the bottles because you did not achieve the torques. Furthermore, torque readings and monitoring the torques and logging them allows you the capability to review your batch records over time. And with this, it highlights the importance of applying consistent and repeatable torque for induction sealing. I'd like to hand over the presentation at this stage to Jeff LaGrange from Enercon.
Thanks a lot, Alan. Now that we know all about the liners and the caps and the cappers, it's time for the rubber to really hit the road and actually create a seal. Keep in mind that every application is a little bit different and has its own challenges. You need to understand how and why you get the best seal. We're going to summarize the steps to help you determine where your sweet spot should be to ensure you get a good seal every time. A more detailed explanation of this summary can be found on our website if you need it. There are 5 basic steps when determining your sealing window. First, you have to make sure your system is set up properly. Next, you check all of your variables. Many of these have already been covered. Third, you need to find the lowest output where you can get a good seal. That's your minimum. Next, you find your maximum where you can get a good seal. Together, these 2 points define what we refer to as your sealing window. Lastly, you select your production output setting and record your data for future reference. Okay, first you have to make sure your sealing head is aligned properly. If not, you just won't get even seals. Your bottles have to travel down the center of the sealing head. We provide stickers on all of our sealing heads to aid in this process. You may find that you need guide rails under the sealing head to ensure proper travel. Next, you need to set the air gap, which Ryan has referred to earlier. He also mentioned that we provide a gap gauge with every system to help you with this process. Make sure you've got an even air gap all the way across the coil, and we recommend a 1/8 inch gap. As Ryan said, consistency is very important. One small exception to the standard bottle down the center of the coil rule is our older #1 universal coil. See a picture of that on the left. As you can see, this coil pivots as the containers get larger, so you're no longer following the center line stickers on the coil. We've got detailed instructions on how to set up this coil in the manual and with an additional sheet that goes with each one of these systems. On the right, you see our newer all-in-one coil designed for the Super Seal Touch. It's got a more user-friendly one-handed internal pivot, which is much more simpler for the operators to use. Now that you've set up your sealer properly, you need to check and be aware of all the other variables that can contribute to seal quality. As you can see, many of these have already been covered, so I'll only touch on them briefly. First, you need to make sure that you run any tests at your production conveyor speed. Next, ensure your liner and container are compatible for a good seal. You ensure your container and caps are free from defects, and verify that your application torque is within acceptable ranges. Once you've taken care of all of these things, you're ready to run some containers and find where your sealing window lies. We recommend that you start at a low power setting and work your way up until you just start to get an acceptable seal. This is what you can consider your minimum set point for your sealing window. From there, slowly increase the output until you just start to see unacceptable signs of scorching. When you see that, you realize you've gone a little bit too far, so you can back up until you see a good seal again. This is considered the maximum set point of your sealing window. Now you've determined where you can get a good seal, but you'll have to choose where within that sealing window you'd like to set your sealer for production.
Hey, Jeff, this raises a question. As you're talking about this, and in the last example, we showed some numbers, and it looked like it was a minimum set point of 55 and a maximum of 75, which would show a pretty big window. Are all applications that wide of a window?
That's a good question, Ryan. No, they're not all that large of a window of 20% as shown on those slides. That was just an example. Some applications will have a wide window like that, while others, depending on many different scenarios, can have a smaller ceiling window of maybe only 5% from minimum to maximum. But each one is different, so you have to run these tests to find out for yourself. So once you've got your ceiling window set, you need to find your location within it. Some people like to put their production level right in the center of the ceiling window and consider that the safest spot. But perhaps your application, you're not really too concerned about a little bit of scorching, and you'd rather be on the higher end of your ceiling window because you'd rather have a little bit of overheating as opposed to a weaker seal. This will allow you to compensate for variables such as bottle height tolerances and variations in torque application. Whatever set point you choose, you should now record all of your important information for future reference. Enercon can provide you with a checklist of sorts, as well as a good spot to record any other data. If you have one of our Super Seal Touches or a new Super Seal Max, these units have provisions to store some of this information on board the sealer, making things much simpler for you and your operator. With all of this, of course, we assume that you're familiar with what you need to look for in determining whether you have a good seal. Keep in mind that there are no ASTM guidelines for determining a good seal. Typically, each company will set their own standards that they need to meet to consider a seal good. These will vary with every application. Here are some things to look for in a good seal. Usually you can use a simple visual inspection. A good seal will have no discoloration on the seal or any backing material. There will be good adhesion all the way around the land area, which you determine when you peel the liner off. There will be little or no wrinkling of the liner. A two-piece liner gives another piece of evidence. You can check the backing material that's left in the cap. Any discoloration here would also indicate overheating. Beyond visual inspection, there are many other ways to check for a good seal, and your company will want to decide what is best for them. There are both wet and dry vacuum chambers that you can employ to check for leaks. Take into consideration how your product will be shipped. Some companies have actually shipped a test run of their product to a certain location and evaluated the seals after they reached their destination. There are also inspection systems on the market that will test for leaks. These usually involve applying mechanical pressure to the container. Lastly, you can be like this guy and shake, squeeze, or stand on your container. I'd say that's a pretty good seal in that container. At Enercon, we've got a submerged vacuum chamber for testing for leaks. We work with customers and in conjunction with their specs to determine if their seal is up to their standards. Keep in mind that some liners will continue to set up for up to 24 hours. Contact your liner manufacturer for this type of information. I learned this the hard way on my very first startup over 15 years ago, where the customer was checking the seal immediately after sealing. But as long as you're aware of all your variables, this really shouldn't happen to you.
All right, thank you, Jeff. Before we get to the questions, we'll take a quick review at some of the topics that were covered today in summary. We learned that pressure, heat, and time are certainly essential for successful induction sealing. We've learned that selecting the right liner is based on its desired function and obviously compatibility. You should consider value-added features for both marketing and packaging security when selecting your liner. It's important to ensure that your cap, liner, and bottle are compatible for both process and function. It's important to recognize the capabilities of your capper and apply either electronic or manual quality control to ensure that your torque is consistent. And as you heard from all of our panelists today, torque is the #1 sealing problem associated with the caps. And Jeff just went over how to set an operating window for each of your induction sealing applications. With the email that you will receive that will enable you to download the webinar, you will also receive links where you can request a cap gauge, a technical guide to successful sealing, and also some of the setup logs and checklists that you can use to help improve your process. We do have some time left for questions, so we're going to begin to address those. Again, we appreciate everyone's time online today. And it looks like the first question we have, Alan, this would be for you. How can one guarantee that no untorqued containers are exiting the capping system?
Great. That's a good question, and typically it's a combination of 3 things. What you want to do is make sure that you're applying the cap correctly, so proper application, and that is done with proper setup of the machine. You want to also make sure that you have an inspection station incorporated into the machine. Typically where we like to put that is between the first and second station, between the application and the torquing station. And with that, you're able to reject crooked caps before the torquing station applies them. Typically that causes some damage to the liner if you try to correct that with the torquing station. So what we like to do is reject crooked caps in between the 2 stations. And last but not least is benefiting from the diagnostic capabilities of a servo torque application. It's not always possible. However, if a servo torque is on the machine, then you'll benefit from a low torque where there's a chuck wear or a grip wear, or if it's stripped cap, you're able to reject the cap without any risk of allowing it to go downstream.
Thanks, Alan. Tim, this question is for you. What is the best method for liner retention?
Oh, that is a good question. There's a lot of that's going to depend upon your application, whether or not you're trying to use an induction seal or if you're just simply trying to seal your package with a foam liner or a pressure-sensitive liner. From our perspective as a cap manufacturer and our tech service team, what we see is that when you're using an induction seal, the best results are going to be achieved if the liner is being held in the cap via friction fit, whether that's with a retention well or if you're using tabs and retention beads to keep that liner in the cap. By using a friction fit liner, it allows the liner to contact the container and still allow the cap to spin and apply torque. As we mentioned, torque is the key. If the liner is actually glued into the container, as soon as the liner touches the container, it is going to halt its application, and the cap will not be able to apply full torque.
Thanks, Tim. We have a question here. Jeff, we'll direct this one to you. I get isolated incident of scorched inner seal, which seems to be attributed to skewed or cocked caps. Is this the only cause of scorched inner seal, especially if it is limited to half of the inner seal?
Well, that kind of sounds like 2 questions in one. Obviously, a cocked cap is not torqued on all the way, and it may be making contact on half of the liner and not the other half, which would explain why it is only scorched on half of the liner. To say, is this the only cause of scorching? I mean, there are, if you have very insufficient torque, what happens is the bottle actually acts as a bit of a heat sink and absorbs some of that heat. If you don't have that action going on, it will, you could scorch all the way around as well. I hope that answers your question.
Thanks, Jeff. John, we have a question for you and for liners. How can you find out what seal to use for a specific product? For example, a product with a high alcohol content or high pH.
Well, many of these products can be different and test differently. The best thing to do is really to speak with our technical folks. Obviously, our contact information is in this webinar. And if we've used that, done that application before, we'll have the answer. Otherwise, we can do some testing in the lab, but it really depends on your specific product.
Thanks, John. Alan, we have a question. What applications would dictate servo torque application?
It is applications where precise torque control is required, where you cannot allow any, there's no operator intervention after the fact. You don't want to allow any untorqued bottles to continue downstream. Specifically difficult caps such as raised lettering, Yorker caps, tab caps, things of that sort, and any applications where you want to benefit from the diagnostic capabilities of a servo.
Thanks, Alan. Our next question will be for Ryan. How can you inspect if an item is sealed or not?
It's a great question, and one that we get probably every day, if not multiple times each day. The key to the process really is ensuring that everything that you're bringing into the sealer, the induction sealing machine, has proper application torque applied. If you go to the lengths to ensure that you've got good bottle tolerances, the cap and container match well, you've got the right foil, and you have proper application torque, and that all goes through each and every time, you will get a sealed container. Now, I realize that that isn't always possible, so inspection afterwards, really on some liquid products, there are some machines which will actually do a squeeze test of the bottle to see if there's what sort of displacement there is in the bottle. That's a method that you can use, but there is not a single system on the market right now which will inspect and tell will every bottle be sealed.
Okay, we've got a question for Alan. The person says, I have spindle torquers, so can only test off torque. What is the recommended method of determining my on torque from my off torque?
There is a chart that's supplied by cap manufacturers that recommends a certain application torque for any removal torque requirement. And that's typically done with trial and error. So what you would do is make contact with the two spindles with the cap, measure the removal torque with a torque tester after the fact, and either tighten or loosen the grip until you reach the required torque. Removal torque, I mean.
Thanks, Alan. Looks like we're closing in on an hour. We'll try to get you a few more questions. Okay, this one is for John. What is the barrier layer made of?
Typically, it's made of PET, and again, that's really it's there to protect the rest of the liner and the closure itself, depending on the chemical.
Thanks, John. We do have a question if you will receive a copy of this presentation, and you definitely will. That will come in an email as soon as we get this posted online. Okay, here's a question. How can we get the induction gauge or roller that you showed at the end? That's from your company, correct, Tim?
Correct. We're going to be providing contact information at the end of the presentation, correct?
Yes, correct. And also, you'll have an opportunity to also get a gap gauge from Enercon as well. Okay, Alan, we have a question. Can you talk more about retorquing after induction sealing for CR closures?
Yes, absolutely. Once the correct application torque is performed, and then you do an induction seal, the heat process removes the sealing layer, makes it thinner, and therefore the cap is typically loose after it leaves induction sealer. You need to allow for a cooling period before you do retorquing, just to prevent any deformation to the neck or cap. And also, typically that is done for one of two ways: to make sure that the removal torque is achieved after induction seal, and also to make sure that the cap does not come loose in transport. Usually a retorquer is required in that case, where it reapplies the predetermined torque after the induction seal process is complete.
John, I've got a question for you. For the center tabbed lift and peel liner, does that require a special punch to cut the liner or custom closure design to retain the liner in the cap?
No, it doesn't. If you're currently using a conventional one-piece liner and you want to use the more convenient, consumer convenient lift and peel type or top tab type liner, you can use the exact same punch, exact same equipment and insertion. The closure design needs to be no different. However, we would recommend that you, as Jeff has talked about before, the setup is to make sure that your induction window is the same or if it needs to be adjusted.
All right, looks like we have time for maybe one more question here. If we don't get to your question, we will follow up with you via email or phone. Final question here is, looks like this will be for you, Ryan. We are a bottle manufacturer. Do you recommend any specific method to test our neck in order to be sure they will work correctly with a liner?
As far as the land area is concerned, the important piece there is that you want a flat, consistent surface. I think just like we talked about through a lot of this presentation is that it's consistent. You want the surface to be as flat as possible, and realistically the width of the land area can be anything you design it to be. We just need about a millimeter minimum surface to seal to.
Thanks, Ryan. I'd like to thank you all again for your attendance today, and also like to thank our panelists from Bellatrix, Phoenix Closures, Sealig Liners, and Enercon Industries. Please look for the email coming to you within the next 24 to 48 hours, which will give you access to download the webinar, the presentation slides, and give you access to some of the additional handouts that our panelists have for you. With that, we will conclude the webinar. Have a wonderful day, and thank you again.